All right, so hopefully you can all see that. Um, Today I'm pretty excited about the lecture for today because this brings us to my favorite topic, something near and dear to my heart, which is about phylodynamic modeling. But let's start out thinking about sort of where we've come from and where we're going. So 2 weeks ago, we discussed how we can use SIR type epidemiological models to track the epidemiological dynamics of different infectious diseases. And then last week, we considered how we could add stochastic variability to these models to simulate realistic looking data, or to add variability to our models when we're fitting statistical models to real data. This week, we'll look at sort of putting everything back together by looking at some of the phylogenetic methods we considered in the first part of the course, with some of the epidemiological modeling that we've been considering over the past few weeks. So in some ways, this is the culmination of the entire course, and hopefully it will sort of connect some ideas up in your own minds, and it also gives us a great opportunity to go back and sort of review some of the material that we've already seen while moving forward and putting everything back together. So for today, let's start actually where we began at the very beginning of the course, way back in the first weeks of January, when we were just beginning to think about transmission trees and how the epidemic dynamics of a given pathogen would affect its transmission tree. So we started out by thinking about just one infected individual represented by this gray dot here, and that individual would stay infected for a certain amount of time, maybe infect a second individual, and then that second individual would infect others, and through this process of the disease spreading between hosts, we'd wind up with this branching structure that we called a transmission tree, where each infected host is represented as its own branch in the tree, and branching events represent transmission events between hosts. But we recognized almost immediately that we don't actually get to directly observe these transmission trees in molecular epidemiology. Generally, the best that we can do is to sample hosts, sample sequence data or other genetic data from hosts. And we don't even get to sample every host necessarily. So what we wind up with is genetic or sequence samples from a subset of all infected hosts, but we could use those genetic samples to reconstruct a pathogen phylogeny. So we spent a lot of time in those first couple of weeks kind of thinking about the relationship between the underlying pathogen transmission tree and the phylogenetic tree that we could then reconstruct from the pathogen sequence data. And our sort of fundamental insight here was that while the phylogenetic tree is sort of an incomplete record of the true underlying transmission tree, it still does sort of retain some useful information about the underlying transmission tree, in that the phylogenetic tree still shows something about the relationships among sampled hosts in terms of who might have infected who. And it also captures information about the timing of particular transmission events. Our fundamental bit of theory here was that the coalescent events, or the branching events that we observe in the phylogeny, could be thought of as basically transmission events occurring between host and the transmission events when we sampled both of the descendant lineages arising from a particular transmission event. So in the underlying transmission tree, a parent would infect a child, and if we then sampled the parent and child lineage and then reconstructed the phylogenetic tree, the transmission event between parent and child would show up as a coalescent event in our phylogenetic tree. Later, as we moved on in the course, we sort of realized that this wasn't strictly true. In lecture 5 or 6, we started thinking about these transmission trees a little bit more carefully, and we recognized that there's also this within host genetic diversity that has the potential to tremendously complicate things. And the exact relationships among individuals in the phylogenetic tree will depend on the exact order at which coalescent events occur within particular hosts. We also sort of recognize that it's a bit of an approximation to say that coalescent events occur exactly at the time of a transmission event between hosts, because we recognize that while at transmission events, a given pathogen lineage might move between two hosts, different hosts can remain in the same infected host for a while before they coalesce. So the physical coalescing event that actually corresponds to the replication of two different pathogen or a pathogen lineage replicating itself and having two different descendant genomes might occur actually sometime before the actual transmission events that we like to be able to reconstruct in our transmission trees. But nevertheless, if we made some approximations, if genetic diversity wasn't too high within individual hosts, and there was rather strong genetic bottlenecks when the pathogen lineages were transmitted between hosts, we sort of recognized that overall this assumption about coalescent events corresponding to transmission events between particular hosts was a reasonable assumption to make, especially if we're looking backwards in time. If we're tracking the genealogy or descendants of a particular lineage, a particular pathogen lineage backwards through time, that those pathogen lineages are going to be moving between different infected individuals. But what has to happen in order for two different pathogen lineages to get back into a particular infected host and then coalesce is that a transmission event between two hosts has to bring those two different pathogen lineages back together. So when we first started thinking about these backwards in time coalescent processes, we weren't too worried about the complexities of the population dynamics going on in the epidemic. We started out by thinking about these very simple population genetic models like the Wright-Fisher model. And if you recall, we were able to use these Wright-Fisher models where basically the entire population reproduces each generation and reproduction is entirely random, to figure out what the probability is of any two lineages coalescing at a particular point in time. And we realized that that probability of two lineages coalescing in a particular generation is equal to 1 over n, or 1 over the population size. And then we can also think about this in continuous time and think about this probability of coalescence as rates of coalescence per unit time, and that rate of coalescence would also be equal to 1 over the population size, or 1 over n, and that the amount of time that we would have to wait for two lineages to coalesce, or for two lineages to find their most recent common ancestor in the population, was exponentially distributed according to this coalescent rate, lambda. And this little bit of theory, while incredibly simple, was very useful to us because it allowed us to develop these coalescent models that we could then fit to phylogenies and estimate things like effective population sizes. For example, we were able to compute the likelihood of a particular phylogenetic tree using this Wright-Fisher coalescent model. And here, basically what the likelihood was the product of a bunch of exponentially distributed waiting times. So we could find the effective population size, or the size of the population that maximized the likelihood of the tree in terms of the population size that gave the waiting times between coalescing events the highest probability. So we could use this basic theory to estimate things like the effective population size, and even how population sizes were changing over time. So we could estimate growth in a population over time or decline in a population over time from how the timing of the coalescent events was distributed over time. The greater the rate of coalescence, the more likely that the population was small, and so we could infer changes in population size that way. And back in week 5, we even used these simple models to reconstruct the seasonal population dynamics of influenza A in North Carolina using these Bayesian skyline plots. But now we've become much more sophisticated in our epidemiological modeling, and it's gotten to the point where we can actually go back and ask if these simple types of population genetic models, like the Wright-Fisher model, are actually appropriate for any given infectious pathogen. And so 2 weeks ago, we considered these SIR type epidemiological models. And these gave us some basic insights into the epidemic dynamics of different infectious diseases, including that the transmission rate of any given pathogen. We can think of the transmission rate as the rate at which new infections are being born through time. Really depends on the overall incidence of the disease in the population, the rate at which transmission events are occurring, which depends in turn on the number of both susceptible and infected individuals in the population, because an infected individual would have to come into contact with a susceptible host in order for a transmission event to occur. That was the basic feedback in the model, that an infected individual would have to come in contact with a susceptible individual for transmission to occur. And so even under this simple SIR model, we get relatively complex dynamics where the epidemic grows rapidly and then starts to decline as there's this depletion of susceptible individuals. So already we sort of know that the transmission rates, or the rates at which new infections are being born into the population, is no longer just a simple constant rate through time, but depends on these epidemic dynamics that's going on in the background. And so we can then actually ask what the rates of coalescence would be for two pathogen lineages under such an SIR type model. And this is actually fairly simple to do, although my approach sort of differs from what's out there in the literature. So there's a couple different ways that you can derive a coalescent model for a given infectious disease from these SIR type models. The approach that I'm showing you today is sort of my own intuitive way of doing it. That's far less formal than what's in the literature, but it's the way that I've been thinking about it for a long time, and I think it just makes quite a bit of sense. So I hope it makes sense to you as well. But basically, what we can recognize right away, starting from first principles, is that two basic things need to occur in order for two different pathogen lineages to coalesce under an SIR type model. First, a transmission event has to occur somewhere in the population, and then the lineages involved in that particular transmission event have to be the lineages that we're tracking backwards through time. So let's go into more detail about these two requirements one by one. So the first thing that has to happen is that a transmission event needs to occur somewhere in the host population. And again, the intuitive reason behind this is that transmission events are what's allowing lineages to, well, if we look backwards in time, we need a transmission event to occur in order for two different lineages that are currently in two different infected hosts to sort of merge back into one parent infected host. So we can reason to start that a transmission event needs to occur somewhere in the population in order for a coalescent event to occur. And the other way of thinking about this is that every time a transmission event occurs between two hosts in the population, two different pathogen lineages are coalescing somewhere in the population, but those might not necessarily be the lineages that we're interested in or the lineages that we're tracking in our phylogenetic tree. So we're not so much interested in what's the overall rates of coalescence in our population as so much as what's the rate at which two individual lineages in our population coalesce. So skipping ahead here, the second requirement then is that of all of the different pathogen lineages in a population that could coalesce at a particular transmission event, our two pathogen lineages that we're tracking backwards in time need to be the two pathogen lineages actually involved in a given transmission event. So as we saw before, at a transmission event, an infected host infects a susceptible host, and then the result of this transmission event is that there's now two infected hosts instead of a single infected host. And so immediately after a transmission event, there'll be two infected hosts. And what has to happen for two lineages to coalesce is that our two lineages that we're interested in, the pair of lineages that we're tracking backwards through time, needs to be in these two infected hosts involved in a particular transmission event. And it's quite straightforward to compute the probability that a particular pair of lineages is involved in a particular transmission event. We know, for example, that the overall number of pathogen lineages in our population is the same as the overall number of infected individuals in that population, because again, we're making this assumption that there's only one pathogen lineage in each infected host. So there's a total of I infected individuals and therefore pathogen lineages in the host population at a particular time. So then we can compute the total number of pairs of pathogen lineages in the population. And that will just be I choose 2, which is the binomial coefficient. So in combinatorics, the binomial coefficient is the way of dividing any number of individuals into a set number of pairs or triples, but we'll just consider pairs here. And so that binomial coefficient then is just equal to I times I minus 1 over 2. And so that gives us the overall number of pairs of lineages or infected individuals that could have coalesced in the population. So if we're interested in the probability of our particular pair of lineages coalescing, that probability will just be equal to 1 over the total number of pairs, which is equal to 2 divided by I times I minus 1. But we almost always consider that the total infected population size is generally much greater than in 1. And in that case, we can approximate this term just by 2 divided by I raised to the second power, or I squared. So we have a simple expression then for computing the probability of two lineages, a pair of lineages coalescing in any particular transmission events. So we can then put everything together. We know that the overall rate of transmission events in the population is equal to the transmission rate, beta S times I. And we know that the probability of a particular pair of lineages coalescing in the population is equal to 2 over I squared. So putting everything back together, then we can then multiply the overall rates at which lineages coalesce times the probability of our particular pair coalescing at that transmission event to get the pairwise coalescent rates, lambda, which will just be equal to 2 times beta times S times I over I squared. But one of the i's in the numerator and denominator cancels out. So what we're left with for the expression for the coalescent rate is just 2 times beta times S over I. So this is actually, it turns out to be pretty interesting, I think, because before, under our simple coalescent models that we were using, for example, the ones that were derived from the Wright-Fisher model, the coalescent rate was equal to 1 over the population size, or 1 over n. And so all along, we've been sort of interpreting the population size of an infectious pathogen as the number of infected hosts. And this turns out to be actually true under these SIR coalescent models. The rate of coalescence will be equal to 1 over I, or 1 over the infected population size. But we were off by an important factor because we weren't considering the overall rates at which transmission events were occurring in the population. And as we've sort of seen before, it's actually fundamentally necessary for a transmission event to occur somewhere in the population in order for two lineages to coalesce. So this brings up a couple of interesting points about the coalescent model for these SIR type models. The rate at which two lineages coalesce is no longer just dependent on the infected population size or the prevalence, but it also depends on the transmission rates in the population as well. This means, unfortunately, that there's no simple way of going back and forth between an effective population size that we would estimate under, say, a Wright-Fisher coalescent model and the number of infected individuals under an SIR type model, as was pointed out in this paper by Simon Frost and Eric Bowles from about 10 years ago. But fortunately, what turns out to be the case is that even though we've been sort of off all along by a factor when we were using these simple coalescent models because we were ignoring the rate at which transmission events were occurring, this doesn't actually turn out to be such a big deal when we try and estimate things like the epidemic dynamics of a pathogen through time, because the incidence of a disease or the rate at which transmission events occur is always going to be pretty tightly correlated with the amount of prevalence in the population. The more infected individuals there are in a population, most likely the higher incidence is going to be too. So we can then ask if this really matters. Would inferences of the population dynamics through time under our SIR coalescent model differ substantially from inferences under our simple Wright-Fisher coalescent model? And the answer is pretty much no. And the reason why is that if we look at both prevalence, which is shown in the blue line here on top, and incidence for, say, an SIR model where there's seasonally fluctuating epidemic dynamics, prevalence and incidence are always going to be highly correlated with one another, right? These two things track each other. There's some lag in terms of prevalence peaks slightly after incidence peaks because individuals need to get infected at a transmission event before incidence or before prevalence can increase, but these two things are tightly coupled to one another. So then if we look at the coalescent rate under one of our SIR coalescent models, which is shown here in the blue in the second plot below the top, versus the coalescent model under the Wright-Fisher model, we also see that the coalescent rates are highly correlated through time. And so if we infer the infected population size under our SIR model or under a Wright-Fisher model, we more or less always estimate the same population dynamics. So the key thing here isn't so much that by using these simpler coalescent models, we've been terribly wrong all along. The key thing here, though, is now that we have this theory for how to fit a given SIR type model to a pathogen genealogy, we can do far more complex things. We can not only estimate how the number of infected individuals are changing over time, but we can also estimate other important epidemiological parameters from pathogen phylogenies, as we'll see. So really what makes these coalescent type SIR models so powerful and important in molecular epidemiology is that they really give us the power to fit any given epidemiological model directly to pathogen sequence data via a phylogenetic tree. And we'll sort of, in the rest of the lecture, sort of generalize the model that we just looked at to allow for any given SIR type model to be fit to a phylogeny. But here, I think this is a good pausing point, and so I'll just ask if there's any questions about the SIR coalescent models. If not, then I will move on. Okay, so one thing we need to be able to consider in order to truly generalize these types of SIR coalescent models is that in reality, in the real world, almost all host populations are structured in some way. You know, for animal and plant infectious diseases, host populations are often strongly structured by spatial factors, such as just the organization of different farms or fields across a given landscape. And even for human populations, where there's generally a high degree of mobility, there can still be spatial or geographic structure, between different cities or between different countries. And then there can also be a high degree of strong population structure even within a given host population due to how individuals interact with one another. There can be sort of assortative mixing where maybe individuals of different ages or different socioeconomic status, say, interact with each other in different ways. And so this assumption of the SIR model that everybody is just sort of randomly mixing with one another quickly falls apart. And so, as we said, when we were thinking about population structure, back when we were thinking about simple coalescent models under the Wright-Fisher model, the thing that makes population structure such a problem for coalescent-based inference is that it violates this basic assumption that all lineages in the pathogen phylogeny are exchangeable or can be treated as identical, because different lineages can be in different populations or different demes, different local geographic regions. And so different lineages in different subpopulations might not necessarily have the same probability of coalescing with one another. So what we need, both for our epidemiological models and then as well as our coalescent models, are models that allow us to really explicitly take into account different forms of population structure. And so 2 weeks ago, when we were talking about SIR type models, we talked about this idea that these compartmental SIR models could easily be extended to include other infected classes or different infected compartments. For example, here in this 2-class SIR model, we have 2 different types of infected hosts, type 1 and type 2, that could correspond to, say, different age groups or different localities. And then transmission events can occur both within these 2 populations as well as between these 2 populations. And so what we would like to be able to do is formulate the same type of SIR type coalescent model that we just developed for the simple SIR model without population structure for these more complex structured SIR models as well. And unfortunately, the hard work has already been done for us. Eric Voles, in this very important sort of key paper from Genetics back in 2012, derived what a structured coalescent model, a general structured coalescent model, would look like for a population that is also undergoing relatively complex population dynamics, like under an SIR model, where there's changes in the rate at which individuals are being born or die over time. And under this more general model, the pairwise rates of coalescence that he derived was equal to this. The rate at which any two lineages, I and j, coalesce is equal to this expression, which looks bad and kind of mathematically gnarly, but we can sort of break this down into its component terms. And we can see that it's actually very similar to the SIR model for the unstructured population that we just derived. Okay, so the first thing that sort of makes this expression for the pairwise coalescent rate look particularly complex is that we have this double summation over all populations out front here. And the reason why we need to include this double summation is that really what we're trying to do here is figure out the rate at which any two pathogen lineages would coalesce going backwards in time. But each one of those pathogen lineages can be in any one of our host populations. So here we have m possible host populations, and each one of our lineages can be in any one of those m populations, or they might also be in the same population, but we don't know. So we have to consider the location of both of those lineages, which is why we get this ugly looking double summation up front here. The next thing that has to happen in order for two lineages to coalesce is that there has to be some birth or transmission event that brings two daughter lineages back together into a parent lineage. And so for our simple unstructured SIR coalescent model, we saw that transmission events were required to occur in order for two lineages to coalesce going backwards in time. And the same thing for these structured coalescent models, except now transmission or birth events can occur not only within individual populations, but they can occur between populations as well. So one lineage could be in population K, and the other lineage could be in population L, and they could coalesce because there was a transmission event between population K and population L. We also have to consider, as we did for the simple SIR model, the total number of pairs of lineages in the population that could have coalesced at a particular coalescent or at a particular transmission event. And what this Y, K, and YL term here, what they represent is sort of a general way of representing the population sizes in populations K and L. And what Y, K, YL represents is the total number of pairs that we could form between individuals in population K and population L, similar to the I squared term that we had in our simple unstructured model. And then finally, we have to consider that we don't actually know where these individual lineages are going backwards through time. We can only track where these lineages are probabilistically. And so we have to take into account that these different lineages, this pair of lineages can be in different populations. So in the term in parentheses here, the first term gives the probability that lineage I is in population K, and lineage J is in population L. But we also have to consider the sort of inverse or opposite situation where lineage I is in population L and lineage J is in population K, because those represent all the different ways that these two lineages could coalesce at a particular birth or transmission event between populations K and L. And then to summarize, then we would then sum over all possible pairs of populations K and L to get our overall coalescent rate. So this is quite complicated, but it's really just generalizing the SIR model for a simple unstructured model. So what does this actually look like for an SIR model where we have different infected populations and there can be transmission events both within and between populations? Well, we can sort of plug in the appropriate expressions from our SIR model into our coalescent rate. And what we see here is that the overall rate at which transmission events occur is beta SI, and we've replaced the generic population sizes with the number of infected individuals in populations K and L. So again, this denominator here is giving us the total number of lineages that could have coalesced at a given transmission event. So the really interesting thing about this model is that, sorry, I'm jumping ahead. As I said before, the thing that makes this model sort of difficult to deal with is that we don't know where lineages are going backwards through time. Any lineage could be in any particular population. We might observe what population an individual was in at the time of sampling, but now that we're tracking these lineages going backwards through time, these lineages are moving between populations, and we can only really track where a given lineage is probabilistically. So I briefly showed you this when we were looking at the structured coalescent models back in I think that was week 5 or week 6. But hopefully now that we've spent some time thinking about differential equations, this will make much more sense now. So I'm showing it to you again. The way that we track where lineages are going backwards in time probabilistically is using this set of master equations, which is really just a system of ordinary differential equations that tracks the probability of each lineage I being in each possible state k. And what's sort of neat about these differential equations that we can see is that as with the other differential equations that we were looking at to track sort of the rate at which the number of infected individuals changes over time, or the rate at which sort of water enters or leaves a bathtub, these differential equations for how the probability of a particular lineage being in a particular population changes over time follows the same basic format of the total rates of change being sort of the rates of flow in minus the rates of flow out. So the first term in parentheses here is the rate at which sort of probability flows into a given compartment, and the second term is the rate at which probability flows out of a given compartment. And so probability here is flowing in or out of a given compartment because lineages can be migrating or moving between different populations. So what these terms represent here are the rates at which lineages are moving between populations, and then how the overall probability of a lineage being in a particular population changes over time is governed by these ordinary differential equations. So the key point here then is that we can then solve for these probabilities at any particular point in time and find the probability of a particular lineage being in a population going backwards in time. So for example, if we had a 2-population SIR model where we had sort of an external population and then a local population that we were interested in, we could actually track the relative probability of every single lineage in our phylogeny being in either one of these populations, and either being in the external population or the local population, using these master or ordinary differential equations that were on the last slide. And so we can actually see how the probability of a given lineage being in a particular population changes over time. And here in this particular population, the probability of all lineages being in the external population basically becomes higher and higher as we go back farther and farther, because the epidemic dynamics, or the epidemic starts in the external population here and then later seeds the epidemic in the local population. So if we go back farther enough in time, we know that all the lineages must be in the external population because there's only any infected individuals in the external population. Okay, so as I started to say a couple slides ago, the really interesting, nice thing about these models is that they don't just work for a particular form of the SIR model. We can basically take this structured coalescent model and derive the appropriate coalescent model for nearly any type of SIR model with almost any form of population structure. But to make this completely general, we have to consider that basically there's 2 fundamentally different ways at which lineages can move back and forth between different populations. So a given lineage can move between two populations due to a transmission event. A lineage can be transmitted from one population into another. And since these transmission events really involve two different lineages, a parent and a child, what can happen at a particular transmission event is a coalescent event can occur. Two lineages can coalesce at a given transmission event. But we can also consider that lineages can move between populations in a way which there's no probability of any coalescent event to occur. And that just happens if a given lineage migrates between two populations. But if just a single lineage is involved, there's no way that a coalescent event can occur. So the key thing here that we need to do in order to sort of generalize these structured coalescent models to consider any form of SIR model is that we have to keep in our minds that these different ways that lineages move between populations are conceptually distinct. And so to help us do that, we can represent the ways that which lineages move between two different populations using two different rate matrices. So we'll let the matrix F here represent the rate at which lineages are moving between different populations due to birth or transmission events. So here, each element in this rate matrix gives the rate at which, say, a given lineage moves between populations 1 or 2, or populations 2 and 1 due to a transmission event. And the same for movement due to migration events that occur independently of transmission events. We can keep track of the rate at which a given lineage moves between populations due to these migration rates. And the logic for keeping these things distinct will become hopefully apparent in a couple of slides. So to make this a little bit more concrete, we can think about specific forms of our SIR type models and think about what would be the appropriate F and G matrix for these models. So let's first think about our two-class SIR model with two different infected compartments. Here again, we have transmission both within a particular population as well as transmission across populations too. So lineages can move back and forth between different populations by individuals transmitting between these different populations. So we can look at the F and G matrices for this particular SIR model. And we can see that the elements in the F matrix correspond to the transmission rates or the incidence between different populations for both the transmission within populations, which are on the diagonal here, as well as transmission between populations, which are on the off diagonal. So for example, the top right element here would give the rate at which a lineage moves between population 1 and 2 due to transmission events between populations 2 and 1. And in this model, there doesn't necessarily have to be any migration of infected individuals between populations due to migration events. For example, if this is a highly structured population where individuals simply don't move between different populations, the migration rate matrix, or this G matrix, would just be a bunch of zeros. But we can also relax this assumption. We could also consider an SIR model in which infected individuals, say, move back and forth between different populations for work or school. And so we could also consider an SIR model where there's movement via migration rates between these two populations. So that was one example of how we can take a given SIR model and turn it into these F and G matrices. Just to give you another example, we can also consider the SEIR models that we considered last week when we were doing our simulations with master. So here, these SEIR models represent, also include an exposed but not yet infectious class, which sort of individuals have to transition through before they become infectious themselves. And so in our differential equation model, we include this incubation period by having there basically be a rate at which exposed individuals incubate into the infectious compartment. So now we can think about what our F and G matrices would look like for this type of SEIR model. And in this case, it turns out to be relatively simple. So here, in the F matrix, we'll have the E class be the first row in the first column, and then the I class, the infected class, be on the second row and second column. And under this SEIR model, infections or transmission events can only occur from the infected class because exposed individuals can't transmit. So there's only one non-zero element in this rate matrix, and we'll put that in the lower left corner because this is the rate at which infectious individuals transmit and cause exposed individuals to become, or cause a sort of a birth of an exposed individual. And then for our migration rate matrix, the rate at which individuals are moving between populations independent of transmission events or births, we have to consider that individuals in the exposed compartment can move into the infected compartment as they incubate over time. And so we'll put that in the upper right corner of the matrix because this corresponds to the rate at which an individual lineage can move from the exposed compartment into the infected compartment. Okay, so the logic behind all of this madness is that for any given SIR model, as long as we can take our model and sort of decompose it into its component F and G matrices, the matrices that correspond to birth or transmission events between populations, and then migration events between populations, we can then derive very simply and very easily what the appropriate coalescent model is for our SIR model. So it's almost as if we have basically a generic formula that we can just sort of plug in our particular type of SIR model into and figure out what the appropriate coalescent model is under that model, which makes this general framework very exciting and can easily be extended to include almost any form of population structure. And the reason why we've needed to keep the birth events occurring in the F matrix distinct from the migration events in the G matrix is that under this general model, again, we have the overall rate at which lineages will coalesce, which will depend on the rate at which transmissions occur between populations, which is this FKL term here that we'll take from our F matrix. And so here, the important thing to note that is that the coalescent rate will only depend on terms in our F matrix, terms that actually represent the movement of lineages between populations due to birth or transmission events, events that can actually give rise to a coalescent event. Whereas our G matrix only really enters into how we track the movement of lineages going backwards in time using these master equations, where the rates at which individual lineages will move between different populations will be drawn from this G matrix instead of the F matrix, because this represents movement independent of birth, so movement events where no coalescent events can occur. And the reason why I've been sort of making you suffer through all this theory is that the nice thing about these models is then you could come up with your own SIR type model for whatever infectious disease system that you're interested in, and you could sit down and think about what the appropriate F and G matrices are, And then you could actually fit this model in beasts. So there's this relatively new phylodynamic package for beast2 called Phylodyn that was developed by Eric Bowles and Igor Severoni at Imperial College London. And what this package essentially does is it allows you to fit any SIR type model to a given pathogen phylogeny by specifying the coalescent model for a given SIR model through these F and G matrices. And then the individual elements in these F and G matrices are given through individual XML elements in the input file to beast. So basically, it becomes very simple to fit any type of SIR model that you're interested in to a tree in beast, because then we just have to specify what these individual elements are in these F and G matrices. And we input these rates in these XML elements, very similar to how we put the individual reactions into our XML last week in master. So each one of these individual XML elements has basically what type of event, whether it's a migration or a birth event, and then a source and a destination of these individual events. So here we have that it's possible that an exposed individual moves to the infected compartment via incubation, which we'll assume happens at rate eta. So yeah, instead of actually having to go into beast and actually code or develop your own SIR type model, you can just use this Phylodyn package for specifying any form of SIR model and then fit it to a phylogeny, which I have to admit it's not easy as pie. I mean, it takes some work to think about what the appropriate F and G matrices are and to set up the XML, but it's far, far easier than actually having to go in and develop your own model in base. So really, I think this package is quite nice, and I'm quite excited that it exists. Okay, so the key point here overall, though, is that with these SIR type coalescent models, especially the generic structured models that we've been considering in the last few slides, it's really possible to take any given epidemiological model and then fit it to pathogen sequence data through a phylogeny. And this allows us to not only infer things like population sizes over time, but to also estimate key epidemiological parameters like transmission rates or migration events between different populations. So just to give you an example, and I know we've already discussed this in this class before, but when we discussed it the first time, we hadn't really developed this theory for how these structured coalescent models for SIR models really work. So I'd like to revisit it now. This general approach was the same approach that I used to fit these SIR models to dengue data from southern Vietnam. So if you remember back in the structured coalescent lecture from January, we were interested in whether or not we could reconstruct the population dynamics of dengue in Ho Chi Minh City and the surrounding area. And we sort of developed this simple structured coalescent model to track the movement of lineages between sort of the global population, everything outside of Ho Chi Minh City, and the focal population, which represented Ho Chi Minh City. And then I said that we sort of derived the appropriate coalescent model that included population structure for this model. But really all that we did was we took sort of the Vol structured coalescent approach and figured out what the appropriate rates of movement for these lineages between populations were and plugged it into the more generic formula for the rates of coalescence. And so we could actually then fit our SIR model with population structure to the dengue data from Ho Chi Minh City and the surrounding provinces. And then under this type of structured SIR model, what we did was we were able to actually track the movement of lineages between Ho Chi Minh City and the surrounding provinces. So here, the more red lineages, the higher probability that lineages has of being in Ho Chi Minh City backwards through time. And by taking into account the movement of lineages back and forth from the city into the surrounding provinces, then what we were able to do is estimate our population dynamics, or the prevalence of dengue in Ho Chi Minh City through time. And we first did this using a very simple Bayesian skyline approach that sort of ignored any of the complex epidemiological dynamics or population structure. And if you recall, you remember that we didn't really infer interesting population dynamics other than maybe a little bit of seasonality. But what we found when we actually fit our more complex SIR type structured coalescent model that accounted for spatial structure between Ho Chi Minh City and the provinces, then we were actually able to reconstruct very reasonable seasonal dynamics of dengue serotype 1 in Ho Chi Minh City. So I think this approach, this general approach, is a very powerful way of combining epidemiological models with phylogenetics to not only account for complexities like population structure when we're fitting these models to real data, but also allows us to estimate parameters and variables that we're actually interested in as epidemiologists, such as prevalence or incidence through time, or migration rates between particular populations. So on Wednesday, I want to give you all a chance to do this for yourselves. So we'll actually play around a little bit with the Phylodynamics package in Beast 2. And so the first thing that we'll do is we'll sort of implement the SEI2R model. This is the SEIR model that had both sort of infected hosts that were highly infectious and less infectious. We'll take this SEIR model and put it into Beast through the Phylodynamics package. And then we'll actually be able to test out if we correctly implemented this model correctly by fitting that model to our simulated data from last week, so we can actually test if we implemented the model correctly in Phylodynamics. And then what I'm hoping, although I don't have this working at the moment, but I think I can get it to work, is that what we'll be able to do is we'll be able to take this SEIR model and actually fit it to some new SARS coronavirus 2 data to estimate transmission rates and transmission heterogeneity for COVID-19 from some data from the Seattle epidemic. So the tutorial is not up online yet, but I'm hoping that at the very latest it will be up Wednesday morning. And then as for the other weeks, you're free to do it on your own, but you can also join me at 1:30 on Wednesday and work through the tutorial then, and I'll be available to answer any questions.